Well, today we're going to be talking about escape velocity. Now, escape velocity actually relates to projectiles, and projectiles are completely unpowered objects. So it doesn't relate to rockets launching at all, it just relates to how fast you'd have to launch an unpowered thing like a bullet or a football, how fast it would have to be going for it to completely escape the gravity of a planet. Well, we'll start with Newton's concept of escape velocity. He did a thought experiment. He didn't actually do this experiment. He imagined climbing to a very tall mountain with a cannon and some cannonballs. And imagine if you fire that cannonball, it's going to follow a parabola. If you remember, that's what Galileo was able to discover. If I fire a little bit faster, it's going to go a bit further before it falls to the ground. There's going to be a velocity at which I fire it, in which it's going to be in a stable orbit. Question, of course, some people have is, what holds satellites in the sky? What stops them falling out of the sky? Well, the answer is nothing. They are falling. They're just falling over the horizon the whole time. Now, Newton thought, okay, what happens if you fire it a bit faster, though? What speed would you need to fire it at so it completely escapes the gravity of the planet? Okay, well, let's think about how we're going to answer that question, how fast it's going to have to be to completely escape the velocity of the gravity of the planet. What's the velocity got to be? Well, let's go back to gravitational potential energy. Remember, that was the weird one. The maximum for gravitational potential energy is 0 joules, and every other value below that is negative. And the graph looks something like this. So the further away we get from the planet, the closer and closer, here we are, we're getting to 0. Okay, and so the maximum that we can possibly have when we've completely escaped the gravitational attraction of the planet is when our EP, our gravitational potential energy, equals 0. Okay, so bear that in mind. So what we've got is we've got the gravitational potential energy of the object, and we want to add enough kinetic energy to that, which is a positive number, so that we get to the maximum that it can be, which is 0. In other words, how much energy would I have to put in to get my gravitational potential energy all the way from whatever that minus value that it is, all the way up to 0, which is the maximum it can have? Well, let's substitute in the equations for those. Big G, M1, M2 on R equals, and kinetic energy is half mv squared. Okay, well, these two masses, well, any two of them are the same, M1, let's call that one M1, so we can cancel those two out. So that leaves us with big G, M2 on R equals a half V squared. So V squared is going to be equal to 2 big G, big M on R. So V is going to be equal to the square root of 2 big G, big M on R. And that is our green box. So that is the escape velocity. That's how much kinetic energy an object's going to have in order to completely escape the gravitational attraction of a planet. A couple of things to notice about escape velocity. First of all, it's named incorrectly. It's not actually a velocity at all. Because we square our velocity here, this is actually a speed. And so if I was to fire an object from a planet, it doesn't actually matter what angle I fire it at, as long as it doesn't hit a mountain or something along the way. I can fire it like Newton's cannon horizontally, or I can fire it perfectly vertically up into the sky. It doesn't really matter. As long as it's got the escape velocity, it will eventually, whatever path it might take, it will eventually completely escape the gravitational attraction of the planet. And of course, that is actually very, very fast for any kind of meaningful planet like Earth. It's thousands and thousands of meters per second. If you shot a bullet, if you could manage to somehow get a bullet going that fast, the thing would just vaporize in the atmosphere long before it escaped the planet. So it's not a very practical calculation, but what it does do is it gives us a good measure of how hard it would be to blast off on one planet compared to another planet. So now we've got our equation for escape velocity. What the syllabus wants to do is to think about that in terms of G, the mass and the radius of the planet. Well, let's think about big G first of all. Imagine, now big G of course is a constant in this universe, but imagine if we changed big G, what would the nature of the relationship be between escape velocity and big G? Well, what we're saying there is our escape velocity is going to be proportional to root G. So that's a graph that looks something kind of like that. As big G gets bigger, then the escape velocity is going to get bigger. Okay, let's have a think about that, not in terms of G, but in terms of the mass of the planet. Well, it's going to be exactly the same shape of curve, isn't it? Y is going to be proportional to root x. So again, it's going to look something like that as I increase the mass of the planet. So as the mass of the planet increases, then the amount of escape velocity also is going to increase. Nothing particularly strange there. It's not a linear relationship. It's a root x relationship. That's what it looks like. What if I do it compared to the radius of the planet though? So what I'm imagining here is I'm keeping big G constant like you would. I'm keeping the mass of the planet constant, and I'm basically compressing the mass of the planet down. What is the escape velocity going to look like? Well, this time it looks something like this. It's a y is equal to 1 on root x. Okay, in other words, our escape velocity is proportional to 1 on the square root of r. And what this shows is that the radius gets smaller, the escape velocity gets faster, and it gets faster at an increasing rate. In other words, the amount of velocity I need to escape from a planet as I squish it down becomes enormous. And one of the implications of this is that's what a black hole is. It's a whole lot of matter compressed into a very, very small space, and the escape velocity is so great that not even light is fast enough, and probably not even some of those faster than light neutrinos can't escape from a black hole. So that's how it varies. As g's increased, escape velocity increases. As the masses of the planets increased, escape velocity increases. But as the radius is increased, the escape velocity goes down. And the interesting side of that is as we reduce the planet's radius down, escape velocity goes up enormously. So there we go, that's escape velocity. It's a useful measure to compare, a comparative measure between different planets, how hard it would be to blast off. But of course, it's not a practical velocity. You'd never fire a projectile. Maybe on the moon with an atmosphere you could. And there are some thoughts about using rails and getting something moving along fast enough and then angling those rails up as a way of launching from the moon. Well, that might be practical without an atmosphere, but certainly not practical on a planet like Earth.